Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 12. Computing Integrals with Variable Limits. Numerical integration of integrals with variable limits involves computing the value of a definite integral where at least one of the limits of integration depends on a parameter or variable. In such cases, one can handle the problem using various numerical techniques, such as the trapezoidal rule, Simpson's rule, or more specialized methods like Gaussian quadrature, with adjustments for the variable limits. Consider the following generalized integral, where ux and vx are functions of x. We may still apply standard techniques like the trapezoidal or Simpson's rules, or more specialized methods like Gaussian quadrature, but the integral's limits will change as x changes. Consequently, it is often difficult to determine in advance the number of panels or integration points required to estimate the integral with the desired accuracy. To overcome this problem, the definite integral is transformed into an integral over an arbitrary fixed interval from c to d. By applying the following substitution. Once the integral is transformed, a suitable numerical method is applied to estimate the integral for an arbitrary x. The Gauss-Legendre or Gauss-Chebyshev quadrature methods can be applied due to the considerable computational savings they offer. It is often more convenient to transform it to an integral from -1 to 1 to take advantage of tabulated quadrature in this range so that no further processing is necessary. Let us consider the following integral with variable limits. We will convert the integral to the one with a fixed integration interval and then estimate the integral for x equals 1, 2, and 5. First, we decide on the interval size and the limits. We wish to employ the Gauss-Legendre method. Thus, the integral should be converted to the one from -1 to +1. Then, with ux equals x squared and vx equals 2x squared, the transformation takes the form substituting y and dy into the integral, we find. Or we may write this as approximating the integral with the Gauss-Legendre sum, we obtain the Gauss-Legendre estimates of the integral for n values from 2 to 5 are computed and tabulated. The computed estimates for x equals 1 depict improvement for increasing n and converge to a solution. Notice that the GL4 and GL5 estimates match to 7 decimal places, and that the absolute difference between the two estimates is 2.88 times 10 to the -6. For x equals 2, the original integral range increases with x and spans from 4 to 8. Despite this, the numerical estimates depict good improvement for increasing n and converge to a solution. The absolute difference between the GL4 and GL5 estimates is found to be 2.57 times 10 to the -6. Using the Gauss-Legendre method with a few integration points yield excellent results. For x equals 5, we observe a similar trend. The absolute difference between the GL4 and GL5 estimates is found to be 1.16 times 10 to the -5. With this note, we conclude this lecture. That is all for now. See you next time with another topic. Bye.